Hello, everyone, and welcome to my talk. My name is Shania Channon, and today I will be presenting on behalf of my colleague Jennifer Kadauke and sharing our most recent paper on the properties of spectroscopically confirmed ultra diffuse galaxies across environments, which rolls right off the tongue, doesn't it? Alrighty, let's get started. Now, before I fully jump into the talk, I just wanted to give you a brief agenda overview of the structure for today so we don't get too lost. Firstly, I will give us a brief overview and background to UDGs and the intent of our work, and then we'll move into the fun stuff. So what observations we made, how we got our data, and then through to analysis, and then everyone's favorite, what we found. Okay, let's get into it. So I hear you sort of all internally going, what are UDGs and why do we care? And that is a fair question. So ultra diffuse galaxies, or UDGs, have been documented for quite some time, but have only recently, in 2016, gained a bit of academic fame. So you're definitely forgiven if you're not fully familiar with the concept. So UDGs essentially are these really peculiar systems which have these really large radii, typically around 1.5 kiloparsecs, but incredibly low surface brightness relative to their size, with a magnitude sitting usually around the 24 mag or above. So to put that in perspective, that's like the whole stellar disk of our Milky Way galaxy, with a brightness of something that the Hubble telescope would be struggling to pick up. And we can see that really clearly with our comparison image on the screen here. So very, very low brightness. Now, in the scheme of things, that's pretty strange and goes against our astronomical intuition when it comes to galactic appearances. We usually associate with bigger equals brighter. And so there's been quite a lot of debate around what UDGs actually are and how they're formed. There are two main theories based on current observed trends of UDGs. The first is a failed massive galaxy theory, where a galaxy has done the initial expansion but never really got to the point of building up much stellar mass. And the second is a puff dwarf theory, where a standard dwarf galaxy undergoes several successive feedback episodes and just makes it very slow to form. So now, looking at all of that, we found ourselves asking, do the structures and stellar populations of UDGs vary across their different environments, or are they just all the same? And so that's exactly what we set to find out. Now, the study of UDGs is still fairly niche and quite a new pocket of cosmology. So most UDGs haven't even been closely catalogued or defined yet, and that makes solidifying theories about mechanics and evolution quite difficult. Our intention for this paper is to create a robust catalogue of spectroscopically confirmed UDGs and log their characteristics so we can infer their likely evolutionary paths and mechanics. Now, the earliest work of UDGs relied solely on photometry, and physical size was inferred from the membership of the coma cluster, which is where UDGs were originally observed and thought to be constrained to. We decided to take a step away from the photometry method just because it can yield some unreliable sizing measurements because they are so faint and there's a lot of interactions that can happen. And now, while we do know that UDGs do occur outside of this coma cluster, we've chosen to remain within the environs for this work. Right, so what did we do? Well, first we conducted a long slit spectroscopic test on 23 UDG candidates from the Smudges survey using a large binocular telescope on the 3 separate runs in 2017. We combined this sample with 29 existing candidates from the Smudge survey and 29 non-Smudge survey candidates. We employed a cleaning algorithm that we made to flatten and limit imagery artifacts, and then used wavelet filtering to identify possible candidates. So once we had our possible candidates, they were vetted again with a neural network and parameter fitting to limit any uncertainty. We used various packages to then prepare for analysis in a data reduction pipeline, which got rid of anything nasty, bad pixels, biases, cosmic rays, scattered light, anything that might give a false reading. Again, because these galaxies are so dim, anything bright in the image can really sort of skew our data. In total, we found 44 spectroscopically confirmed UDGs that fit the criteria within allowed uncertainties. And then once we had that list, we moved on and recorded their redshifts using A-type stellar template, which is consistent with the current best practice. Now, once we had these redshift values, we can use that to extrapolate a lot of the remaining characteristics for each UDG. So for each UDG we recorded, we extrapolated the following: central surface brightness, effective radius, axis ratios, absolute magnitude, Cercic index, recessional velocity, and environmental classifications, which was quite a lot, quite extensive. Okay, great. So we recorded all of these parameters. Now, what does that actually translate to in reality? Like, why are these particular measurements so important? Well, our core parameters were our radius and our brightness. Spectroscopic redshift is first used to find the effective radius, so how wide the galaxy is. And then secondly, surface brightness is taken from our imaging pipeline that we made. These are our two key constraints for determining whether an entity is a UDG or not. So fitting into these parameters that we talked about earlier that you can see on the bottom screen here. These are our defining constraints and the minimum requirements our galaxies need to meet to be classified as a UDG. So once they're confirmed as a UDG, we go, yep, they are at least 1.5 kiloparsecs wide and at least 24 magnitude in brightness. We can move on to our structural parameters. So figuring out what the makeup of these galaxies are. So our structural parameters were our axis ratio and our Cercic index, which tells us basically how round or flat the galaxy is. And that can then be used to infer what kind of environment has shaped them. So is there a lot of top-down pressure, a lot of sidewards pressure? We can also use our redshift to determine whether the UDG is a member of the cloma cluster or whether it's just existing in the local environment. Then we can look at our stellar populations. So looking at the colors, we can infer age, metallicity, and the kind of stars that are present, as well as there's still some active formation going on. And lastly, we look around the galaxy itself and just determine whether the local region is dense, sparse, or unconstrained. Now, all that information across our 44 candidates, that was a lot to record. So what did we find? Well, firstly, I just want to have a little look. These are our 44 confirmed UDGs. Aren't they beautiful? And as you can see, they are all very faint and still quite hard to image. So there's still a lot of background noise, even with all of our cleaning and aliasing. So all of these 44, were they any different from one another? Well, in a structural nutshell, not really, which isn't quite true, but it's pretty close. We found no statistically significant differences in the structural parameters for our UDGs across any environment. So whether a galaxy was smack bang in the center of the cluster or way out to the side, the structure of the galaxy itself remained pretty much the same. So between UDGs that were part of the cluster or field, we found that effective radii had pretty similar distributions. Central surface brightness was roughly the same. Cercic index was also pretty similar too. There was a few on either end of the spectrum, but they were still all within the allowed uncertainties. So, and even looking at our environmental density, so around the galaxy itself, there was no significant differences there either. So structurally, UDGs across the board seem to be surprisingly uniform. There were some slight variations in ratio distribution, so slightly different shapes, but nothing statistically robust. Where we did find some differences, though, was actually in the stellar components. We saw a pretty pronounced trend with color versus proximity to the cluster center. We found that UDGs near the center of the cluster were consistently redder, which is indicative of much older stellar populations. And those UDGs that were further out in the sparser environments, so our field galaxies, were consistently bluer, indicating new ongoing stellar formation. And now this is pretty on trend with what's been observed in some of the preliminary smudge surveys for UDG candidates. So to have these now confirmed as actual UDGs is quite exciting and very important for understanding the mechanics and evolution of these galaxies. In terms of what we can glean from that analysis, firstly, the lack of structural differences across the environments suggests that the mechanism that makes galaxies large and diffuse doesn't actually strongly depend on whether you're in the cluster or the field. So UDGs are just large and diffuse by nature. Secondly, the color and UV trends demonstrate that environment proximity, on the other hand, directly affects gas content and star formation. So for those galaxies that we see close to the center of the cluster, ram pressure strips away that gas and it leads to quenching and the red color that we observe. So it stops all stellar formation. And then we see the opposite in our field galaxies where UDGs have a bit more room to breathe and can actually albeit slowly, keeps star formation up and presents us with that blue colouring that we've observed. So what this means, quite importantly for the budding new field of UDG study, is that the proposed theories for evolution we talked about earlier actually might not be one or the other, but we prefer is actually both, depending on whether you are a cluster member or out in the field. UDGs closer to the center of the cluster are UDGs simply because they've been smushed during their formation, or quenched if we want to get fancy. And those that are a little further away are simply slowly evolving dwarf galaxies. So we get the best of both worlds here, or the best of both galaxies, I should say. The penultimate question of how do these strange galaxies form, well, it seems to depend entirely on location, location, location. So finally, we can conclude from all of this that field UDGs are most likely a population of slowly evolving star-forming galaxies, whereas those within the cluster core have undergone rapid quenching, likely due to interactions with a dense surrounding environment. We can also confirm that the structure of UDGs is fairly uniform, regardless of environment. However, the individual stellar populations within those galaxies is incredibly environment dependent. Now, I know I've kind of run through this very quickly, and this is quite a brief talk. So if you would like to know more, have any specific questions, you would like to see the raw data, please feel free to reach out to me on the email on the screen. I'd like to thank you all for your time, and I hope you have a great rest of your day. Thank you so much.